continue with our discussion on the photoionization expression that we had got last time. We had used for analyzing single photon multimode state. I'll give you another example of showing single photon interference, and then we will move on to this topic of balanced homodyning. Okay, so do you have any questions? Our earlier discussion. Okay, let me recall. We had defined the total electric field is actually defined in terms of positive frequency part and a negative frequency part. The positive frequency part is I sigma under root h cross omega L by 2 epsilon 0 V L exponential minus I omega L T minus K L dot R. And the negative frequency part is simply the Hermitian conjugate of this. And we define the photoionization probability at a point R between times t and t plus dt is proportional to this quantity, where this is defined as the expectation value of E minus RT E plus of RT psi. So for a given state of the field represented by ket psi, the probability that you will observe a photoionization is given by the expectation value of this quantity. It is a product of E minus and E plus, and note that E plus contains A operators and E minus contains the A dagger operators. So in this expression, and remember this is the total electric field, it consists of the total electric field of all the modes of the system, and all the creation operators are on the left and all the annihilation operators are on the right. This is called normal ordering. So if you are given a state psi and you know the modes, this is the total electric field, to calculate what is the probability of photoionization, you need to use this expression and get the probability of photoionization, which means what is the probability of photodetection. Now, last time we saw one example where I took a multimode single photon state and we looked at the probability of photoionization and found that this probability is actually moving at a velocity given by c. So all it means, if you form a wave packet where the probability of observing photoionization was maximum at this point at t is equal to 0, then at a later time the probability of maximum photoionization occurs at a different point given by a distance covered at the velocity of light, which is exactly the velocity at which this photon wave packet is moving in free space. So all it means is that if I had a wave packet, multimode wave packet, single photon wave packet, and if I put a photodetector here, that means I have an atom which is spontaneously emitting a single photon. I have n number of such identical experiments. Each one of the experiments measures the time this photoionization takes place here, and I will find a distribution, because not all of them will detect at the same time, because there is a wave packet, single photon wave packet coming. There will be maximum probability at a certain time, and the probability will keep on decreasing as a function of time. And this is in a spontaneous emission, it is an exponential decay. It's a wave packet which looks like this. It starts when the spontaneous emission arrives and then decays exponentially. Now, I want to use this expression to show interference of a single photon, and for this I want to consider the following state. A single photon state, 1 by root 2, 1, 0, plus 1 by root 2, 0, 1. Well, let me call this 1, 1, 0, 2, 0, 1, 1, 2. So modes 1 and 2. Now, remember these modes are defined by propagation direction, polarization state, and frequency. In the earlier examples we looked at, we assumed the same polarization state, same propagation direction, and different frequencies formed a wave packet. Now I want to look at two modes which have the same frequency, same polarization, but propagating in different directions. So for example, I could have a situation where this is the screen where I'm having a photo detector to measure the photoionization, and I could have one corresponding to this mode and one corresponding to this mode. So this could be the mode 1 with propagation vector k1, this is mode 2 with propagation vector k2. And please note that there is only one photon occupying both the modes. It's something like this. If I had, for example, if I could set up a following experiment, I have a mirror here, beam splitter. So I have a beam splitter in which a single photon is incident, this vacuum state from here. This photon produces a superposition state, and then there are two mirrors which direct the beams into two different directions to interfere on a screen. In a Mach-Zehnder, I would have actually interfered them back on a beam splitter, but here I am assuming that these are big mirrors and I can assume these to be plane waves. So I am assuming that this is a plane wave going in one direction, that's a plane wave going in another direction, and I want to find out what happens here. Classically, what would I see? What would I see on the screen? An interference fringe pattern, which will be, depending on the phase difference, it will be maximas and minimas on the screen. So what I will expect is, quantum mechanically I will show you that if you have a single photon incident from here, and if you could measure the photoionization probability as a function of position, you will see a fringe pattern. Which means the probability of photoionization here may be maximum. If you move slightly away, the probability becomes 0. Depends on the amplitudes of these two. Again, it becomes maximum 0, maximum 0. So it is a single photon which is actually coming and creating a state of two modes, each one propagating in a different direction, and I will use this expression to calculate. I'll use this expression and show you that the probability of photoionization shows me the interference pattern. Now, there are two modes only, so I need to look at the total electric field to consist of only two components. Yes, Mohit.
So, the probability of photoionization that we had calculated.
Yeah.
What does it exactly mean? When a photon is incident on an atom, so its probability of photoionization.
Yeah, probability that the ion gets ionized, the atom gets ionized. Because that will lead to a current in my external circuit.
When a wave packet consisting of a single photon is incident.
Whatever, single photon, any complex, this thing, multi-photon, whatever it is.
In our case, what we are analyzing.
Yeah. So this is the general expression where psi could be any general arbitrary electromagnetic state, which could consist of multimode states, different polarization level. Okay. Now this is, if it has different polarization, actually these are vectors. This has to be a dot product here. But we are not going into vector form here. I'm assuming that the electric field has one polarization. Same polarization. So now I had earlier looked at a single photon state occupying different frequencies, a superposition of different frequencies.
So that is why different modes.
They are all different modes, exactly. Now I am looking at a single photon occupying two modes at the same frequency but propagating in different directions. The modes are now different because of propagation direction and not because of frequency. So what will I write for E plus? So it will be I. So it will consist of two terms. Please note that this is the total electric field. I must use the total electric field because the state I am considering is like this. All terms in this sum other than those of the two modes will give me 0 when I operate on psi, because psi contains zeros for all values of the subscript other than 1 and 2. So if in this sum I took a third term, omega 3, AL3, etc., A3, etc., when that operates on psi, any of these, because this is 0, 3, this is also 0, 3, that will give me 0. So I don't have to worry about all other terms in the sum. I need to worry only about modes 1 and 2. So the total electric field that will be responsible for this, the total electric field that will take part in this giving me finite terms here will consist of two terms. The first one will be I h cross omega by 2 epsilon 0 v. I am assuming one frequency, A1 exponential minus I omega t. What do I write now? Minus K1 dot R. Please see here. This is the electric field. This is one term. I square root of h cross omega by 2 epsilon 0 v A1 exponential minus I. Omega is the same. Omega I just call it. And the first mode has K1. And then I have I square root of h cross omega by 2 epsilon 0 v A2 exponential minus I omega t minus K2 dot R. In the problem sheet, I have given a problem in which the two modes correspond to waves propagating in the same direction with the same polarization but at two different frequencies. So I will have to follow the same procedure, except that I will have to have omega 1 and omega 2. Case will be the same. E minus will be minus I square root of h cross omega by 2 epsilon 0 v A1 dagger exponential I omega t minus K1 dot R minus I square root of h cross omega by 2 epsilon 0 v A2 dagger exponential I omega t minus K2 dot R. This is the side, this is E plus, this is E minus. To calculate the probability of photoionization, I need to calculate the expectation value of E minus E plus in with respect to this state psi. So now let me call this chi1, chi2, just to compact to make it compact, and these expressions, the outside multiplication factors are the same. So what I will get is, so W1 will be, so 1 by square root of 2, 1102 plus 0112. Now I have, okay, this factor I under root h cross omega by 2 epsilon 0 v. So let me call this, this is a common factor, and this is the same in E plus and E minus. So I will get an outside factor which I will write later. Okay, so I have A1 dagger exponential I chi1 plus A2 dagger exponential I chi2 into A1 exponential minus I chi1 plus A2 exponential minus I chi2 into 1 by square root of 2, 1102 plus 0112. This is brass I. Okay, this is to be multiplied by, so I have I times h cross omega by this thing coming here, the minus I, so I'll get h cross omega by 2 epsilon 0 b. And chi1 is omega t minus K1 dot R, and chi2 is omega t minus K2 dot R. Brass I, E plus, E minus, E plus into ket psi. Now I can operate this on the right side, I can operate this on the left side, and get quick expressions. So what happens to this when this operates on this side? Okay, so let me operate these two. So I will get now, so W1 will be h cross omega by 2 epsilon 0 V. So there is a 1 by root 2 and 1 by root 2, so that becomes another factor of 2, that becomes 4. Okay. Now what is A1 dagger operating on this state?
0, 0, 0.
So I'll get 0, 1, 0, 2 into exponential I chi 1. A1 dagger operating on this gives me 0. A2 dagger operating on this gives me again 0. A2 dagger operating on this gives me A1 operating on 0 is 0. A1 dagger operating on bra 0 is 0. The second one, A1 operating on this gives me exponential minus I chi 1 into 0, 1, 0, 2. A1 operating on this second term gives me 0 because this is 0 here. A2 operating on this gives me 0 because the second mode is unoccupied. A2 operating this gives me 0 minus I chi 2, 0, 1, 0, 2. This is vacuum state. Actually, all others are anyway zeros. I'm not writing them here, but 3, 4, 5, everything is 0. So this is 0, this is 0. These are all the same states. So let me open this bracket. H cross omega by 4 epsilon 0 V. So this into this is 1. This into this is plus exponential I chi 1 minus chi 2. This into this is exponential minus I chi 1 minus chi 2. This into this is 1. So this is equal to h cross omega by 2 epsilon 0 V. So I've taken out 2. So 1 plus cos this is 2 cos chi 1 minus chi 2, and chi 1 minus chi 2 is this is k1 minus chi 1 is omega t minus k1 dot r, chi 2 is omega t minus k2 dot r, sorry, this is k2 minus k1. Chi 1 minus chi 2 is k2 minus k1 dot r. So you see here interference. At those values where this is 0, 2 pi, 4 pi, etc., this is plus 1, and I get a maximum probability of photoionization. And whenever the cosine term is negative, minus 1, the probability becomes 0. So for example, in this figure, to be more specific, let me call this z and let me call this x. And let me call this angle as theta and this angle also as theta, just to be a little more specific. So what is k1 vector? This is a plane wave going at an angle theta with the z-axis, like this. And this is another plane wave going at minus theta with z-axis. So what is k1 vector? You have the figure here. So k1 vector is equal to omega by c, which is the propagation constant, into cos theta z cap plus sin theta x cap, and k2 vector is omega by c into cos theta z cap minus sin theta x cap. And if I were measuring the photoionization probability on this plane, which I call as z is equal to 0, then chi1 minus, what is that? Chi1 minus chi2 becomes equal to, which is k2 minus k1 dot r. So you get, this is at z is equal to 0. So what do you get? K2 minus K1 dot R at Z is equal to 0. You will simply get 2 omega by C right. Okay. So chi1 minus chi2 is equal to omega by C cos theta z minus omega by C sin theta x. This is k2 dot r minus k1 dot r, which is omega by C cos theta z plus omega by C minus, yeah. So at z is equal to 0, chi1 minus chi2 becomes minus 2 omega by C sin theta into x. Okay, so I get for the photoionization probability.
Why is it necessary for at z equal to 0?
I'm on the plane. I'm just looking at the typical interference pattern that I will observe is on a plane. So I'm just trying to find out. Otherwise, this is a general expression. At any value of xz, if you place an ion and look at the photoionization probability, it's given by this expression.
No, what I'm trying to say is that chi1 minus chi2 has no z component.
Yeah, anyway, that's fine because of the type of direction which I've chosen. So, which means at any plane, I'll get the same expression. So, what I get is W1 is equal to h cross omega by 2 epsilon 0 V into 1 plus cosine of 2 omega by C okay, so on this screen for example at x is equal to 0 you have maximum probability. If you move away from here so that this argument becomes pi by 2, you get 0. And then when the argument becomes pi, when the argument becomes pi, it becomes 0. When the argument becomes 2 pi, it becomes maximum again. So exactly what you will observe in a classical interference pattern between two plane waves, one propagating at plus theta with the z-axis, the other propagating minus theta with the z-axis. The difference is I have only one photon here. The state psi corresponds to a single photon that is put into a superposition state between two modes, and because it is in a superposition state between two modes, when you recombine them and you find that the probability of photoionization shows interference. So if you perform your experiment, Young's double hole experiment with single photons coming in, you will still see the interference pattern. Of course, you won't see an interference pattern. What you will see essentially is you send one photon, you have a sort of large number of photodetectors sitting here, okay? An array of photodetectors. So one of them will click. Next you send another photon, another one clicks. Third time you send another photon, another one clicks. But the photodetector sitting here will never click. The photodetector clicking here will have maximum number of clicks. So it's like plotting a histogram of the number of clicks. Exactly. So it's like a photographic plate which is sitting there, and I'm sending one photon after another photon, the interference pattern gets built up by detected points.
This is assuming that we have a beam splitter and we have actually created the superposition state. But will we see this if I just have a slit and will there be diffraction if I just send a single photon?
Surely. What that would mean is that if you have a slit and if you send a single photon, it will arrive somewhere on the screen. But if you had n number of photodetectors, large number of photodetectors, and you perform this experiment a large number of times, most of the photons will arrive here. At some angle, there will be never a photon, and the probability distribution will exactly look like sine square beta by beta square pattern.
My question is that the state that we have assumed, will that state result from a diffraction also? So from us, if I pass a single photon through a slit,
it's more than this. From diffraction, it's more than this. From diffraction, it's a continuum of directions. It's like when I look at the single mode multi-frequency state, multi-mode single photon state, I looked at different frequencies present simultaneously. A single photon being present simultaneously in many frequencies. What you are talking is a single photon present multiply in different directions of propagation simultaneously, but at a single frequency. So you get a wave packet in space. A wave packet in time is one which you generate by adding components at different frequencies. You get a wave packet in space by adding waves in different directions and adding them up properly to get a finite beam of size. So what you will generate there is much bigger than this, because this is just a two-mode state. Okay, so actually one can do beyond this point, and because of lack of time in the course, I don't think I will discuss that. But for example, I can calculate things like I put one photodetector here, another photodetector here. What is the probability that both of them detect simultaneously? With a single photon, there is never possible because there is only one photon. But I can have states in which there are more than one photon. There are two more states, for example. I can find out probabilities of simultaneous detection. These are called coincidence counting, etc. And the difference between classical and quantum becomes much bigger there, because here I don't see any difference from the classical interference pattern. It's the same as the classical interference pattern. Although I still have to worry about how a single photon is interfering with itself. How the single photon, which is supposed to be in a superposition state. Because superposition is a very tricky concept because the photon is in simultaneously in both propagation directions. So those probabilities of detecting two photons simultaneously at two different points, or one photon here at one time and another photon here at another time, etc., is much more interesting. But of course, that will not happen with single photons. The single photons, the probability of detecting at 2 points is 0, because once you detect at 1 point, it's not there in the second point. So things like Hanbury-Brown-Twist experiment, etc., they are all based on those kinds of interference effects, which we will not have time to discuss here. Okay, so as I mentioned in the problem sheet, I have given another problem in which you need to take two modes with two different frequencies, but propagation direction is the same. What do you expect? Beats. Okay, so you'll have beats. So if you have a detector here, you will see beats. See beats means what? Please. Again, it is an addition of a number of measurements, because one measurement can only detect one photon at one time, that's all. Okay, so that's the meaning, beats meaning that I repeat the experiment a large number of times and I build up a histogram and I find that I will see certain instants of time when there is no intensity at all. Okay. Okay, now what I want to discuss of the beam splitter, why I did the beam splitter in a little more detail, is because first of all it is very interesting, in the sense that I showed you some interaction-free measurements possibilities with this. And the more interesting thing is that it can be used to detect squeezing. Now please note, when we discussed squeeze states, we showed that we wrote the electric field as a sum of two quadratures, x and y. In a coherent state, the noise in x and y are equal. The variances are equal. Delta x, delta y is 1 by 4. Delta x is 1 by 2, delta y is 1 by 2. So we drew a coherent state like this. I could have a coherent state like this. There is an uncertainty principle which tells me that there is a product of delta x and delta y must be greater than 1 by 4. Greater than equal to 1 by 4. And when it becomes equal to 1 by 4, I get minimum uncertainty states. So x is one quadrature, y the other quadrature. Now, in squeeze states, which we discussed, we showed that it is possible to have a state like this, where delta x is less than half and delta y is more than half. So this product is still equal to half, is 1 by 4. Minimum uncertainty squeeze state. Of course, I could have a product which is always more than 1 by 4, there is no problem. But the minimum is 1 by 4, and I can have state like this, in which x quadrature is squeezed, or I can have a state in which the y quadrature is squeezed. That means the uncertainty in x is less than in a coherent state, the uncertainty in y is less than in a coherent state in the y squeezed coherent state, so a squeeze state. Now, when I normally use detectors, I don't measure one quadrature. I'm measuring the photon is getting detected. I'm actually measuring the total electric field, and I cannot differentiate between, here for example, I cannot differentiate between different phases of the electric field. Now, in order to do this, to be able to measure either the x quadrature or the y quadrature to show that there is less noise than in a coherent state, I use interference effects. I need a phase reference. The phase has to have a reference, and this reference comes from what is called as a local oscillator. So what is done is the following. Let me look at this setup. So I have a beam splitter. This is input 1, input 2, input 3, input 4. I have one detector here. I have another detector here. And I subtract the detections from this detector and this detector. So these are actually giving me expectation values of the photon number. Light is coming here continuously and this is detecting. Now what happens is, okay, here what I send is, this is called the local oscillator. And we send here a coherent state, which means a laser. A laser output is a coherent state. Now let me tell you, those of you who have done electrical engineering may have come across homodyning and heterodyning. This is a very standard procedure which is used in signal processing, where you mix your input signal with another local signal, and it can act as an amplifier actually. It amplifies the signal and it picks up a particular phase of the input signal. You can pick up a particular phase of the input signal by mixing, in electronics for example, a given signal and a signal that you are generating at the local oscillator. If you have the same frequency between the signal and the local oscillator, it's called homodyning. If the two frequencies are different, it's called heterodyning. Okay, so this is the input state which I am trying to find out, which I am trying to measure. This could be the squeeze state, this could be another number state, whatever it is. I'm trying to do measurements on this state, do measurements dependent on phase. So what I do is, I send the state from here on a beam splitter. I have a local oscillator which sends in a coherent state. The beam splitter mixes these two beams in this arm and in this arm. These two beams, which are then falling on two detectors, which detect the photons as they arrive here, and then I do a processing of subtracting this 4 from 3 or 3 from 4, and I will show you that this difference contains information about the phase, about the different quadratures contained in this state psi. I can choose the different quadrature which I'm measuring by modifying the phase of this local oscillator. Now, we have analyzed the beam splitter in a particular fashion. Remember, we wrote the expressions between A3 and A4 and A1 and A2. So we wrote, for example, A3 is equal to I by root 2 A1 plus 1 by root 2 A2, and A4 is equal to 1 by root 2 A1 plus I by root 2 A2. And then what we did was we assumed that the input 0102 goes to 0304 and found out the state coming out of the beam splitter. And here we will follow a slightly different procedure, and the procedure is as follows. It's a Heisenberg picture. So what I will say is the beam splitter modifies, so A1 and A2 at the input get modified to A3 and A4. So I will represent the state of the system by the input state, and all observables at the output will be calculated by expectation values of these operators with respect to this. So for example, suppose I want to calculate what is the expectation value of the photon number in this arm. Okay, so what is expectation value of what should I find out? N3, which is expectation value of A3 dagger A3. I need to know. So what I do is the following. I represent, so this is psi in the first state and alpha in input 2, A3 dagger A3, alpha in state 2 and psi in state 1. Now, I represent the state as at the input, and I will write A3 and A3 dagger in terms of A1 and A2. So what I will have to calculate is psi 1 alpha 2 minus I by root 2 A1 dagger plus 1 by root 2 A2 dagger into I by root 2 A1 plus 1 by root 2 A2 on alpha 2 psi 1. Please note the procedure. So what I am writing is the output operators, the operators corresponding to the output states are represented by in terms of the operators corresponding to the input states. A3 is written in terms of A1, A2, A4 is written in terms of A1, A2, and I assume the for calculating the expectation values, I assume the state that is input into the system. So in this picture, the states do not change, but the operators have got changed, and I can find all expectation values. Now, what do you expect this number to be? Suppose it was one photon here and no photon here. Suppose I took this example and I assumed that psi 1 is equal to 1 and alpha 2 is equal to 0, vacuum state. What would I expect this to be?
1 by 2.
Yes, half. So I leave it to you to show. Please substitute psi 1 as 1. 1 and so the input corresponds to one photon in the input arm 1 and vacuum in the input arm 2. And if you calculate this quantity, you will find half. That is the probability of detecting the average number of photons which will be arriving here. Similarly, N4 will be half. So this is another picture which is similar to Heisenberg picture where operators have got transformed. I express the transformed operators in terms of the input operators. I keep the state vector the same as at the input, and then I calculate all expectation values. If I want to calculate the variance in this photon number measurement here, I need to calculate delta N3, which is N3 square average minus N3 average square. Okay, so all the procedure is exactly the same. Yes, Rajiv.
Inputting a vacuum state is a coherent.
No. Yeah, this is homodyning, but I'm considering another. Before I consider this, I'm considering an example where a vacuum state is a coherent state with alpha is equal to 0. Also, right? So I'm trying to. This is an example I want to use. I want to use this procedure to tell you that this procedure gives me the result that I want in the expectation values, for example. This is different from what we did earlier, because earlier I used these expressions to calculate what is the output state emerging from the weave splitter. Here I am not calculating the output state. I am assuming the states as if they were at the input states. The operators have got changed. The changed operators I write in terms of the input operators and calculate the expectation values. So if I input one photon and vacuum here, I know the probability of detecting photon is half here and half here. So the expected number of photons is half and half there, which is the expectation value. Okay? So this is a prelude to what I'm going to discuss, because I'm going to use the same procedure in calculating the expectation value of the photon numbers here, expectation value of the photon numbers here, which I will subtract when I go through the electronics processing here. Okay, so in the homodyning, so this is called what is called as balanced homodyning. So let me write it again here. This is called balanced homodyning. In which we have the unknown state coming from here. We have a coherent state coming in from here. These two outputs are detected and then processed. This alpha has alpha is equal to mod alpha exponential I phi. There is a phase of this coherent state. By varying the value of phi, I will show you that I can pick up the x quadrature or the y quadrature of this. That means the signal, what I am getting out from here as the difference in the currents between this detector D3 and D4 is proportional to the expectation value of either the x quadrature or the y quadrature or any combination of them, depending on the value of phi I choose. So if I wanted, for example, if this input, at this input I had launched this kind of a squeezed light, I would like to detect the x quadrature, and I will see that depending on the value of phi I choose, I will either measure the x quadrature or the y quadrature or actually any other quadrature which I want, any other orientation.
So what would be an unbalanced version of this?
This is only one. That's a standard homodyning, in which they detect one of them and then process that signal.
Okay.
This is balancing by the other detector. What happens is, in this case, all noise contained here just cancels out. And usually it's assumed, we assume that this is a much stronger field than this one. This is it's a weak field which is coming, for example, squeezed vacuum. I can do measurements on squeezed vacuum coming from here, and I can show squeezing in vacuum. Remember, I had shown in between some sets of plots. They are all by homodyning, balanced homodyning techniques. So you are actually measuring currents here, but depending on the phase that you choose here, you are actually measuring an appropriate quadrature of this input field. And if it has less noise, you will see less noise here. If it has more noise, you will see more noise here in the difference. Okay, I'll just give you a few steps and then we'll continue in the next class. So what I want to calculate is, so what is this doing? This is measuring the expected number of photons arriving here. There's an expected number of photons here, and what I'm doing is subtracting the two. So what I'm actually measuring is this quantity. Sorry, A3 dagger A3 minus A4 dagger A4. A3 dagger A3 expectation value will give me expectation value photon arrival here, and similarly A4 dagger A4 here. And when I subtract, I'm actually subtracting and I'm actually calculating the expectation value of this quantity, because A3 dagger A3 expectation value is here, A4 dagger A4 expectation value is here, and when I subtract, I'm actually getting this difference. So let me just write down an expression, just derive an expression for this, and then we will stop. Okay. So what I do is, because in the procedure we are going to adopt, we will assume the field at the input to be the representation of the state vector, and we will replace these operators by the A1 and A2 operators. So let me calculate what is the expression for ND operator. So for this I need to substitute A3 dagger and A4 dagger. So ND, so A3 dagger A3, so that is minus I by root 2 A1 dagger plus 1 by root 2 A2 dagger into I by root 2 A1 plus 1 by root 2 A2. This is A3 dagger A3 minus 1 by root 2 A1 dagger plus, minus I by root 2 A2 dagger into 1 by root 2 A1 plus I by root 2 into A2. A3 dagger A3 minus A4 dagger A4. Let me expand this. So 1 by 2 comes out from everywhere. So I'll have A1 dagger A1 minus I A1 dagger A2 plus I A1 A2 dagger. A1 and A2 commute. They are two different modes. So plus A2 dagger A2 minus A1 dagger A1 plus I A1 dagger A2 minus I A1 A2 dagger plus A2 dagger A2. A3 dagger A3 minus A4 dagger A4. This cancels off, this cancels off. Minus I A1 dagger A2 minus I A1 dagger A2 plus I A1 A2 dagger plus I A1 A2 dagger. So this becomes equal to I times A1 A2 dagger minus so this operator corresponding to this difference is A1 A2 dagger minus A2 dagger A1. Now, because the input state, one of them I have chosen as the coherent state. So what is the state representing the input? That state is psi in 1 and alpha in 2. So expectation value of ND is actually psi 1 alpha 2 into I times A1 A2 dagger.
Would it be A1 dagger?
Sorry, yeah. I'm sorry. A1 dagger A2. Otherwise, they are the same term. Sorry, yeah.
And are A2 dagger A1 and A1 dagger?
A2 dagger A1.
A1,
It should be A2 dagger A1, the first term.
Yes, A2 dagger.
First term should be A2 dagger A1.
Plus I, yeah, A1 A2 dagger. That's right. That's what I'm writing. A2 dagger and A1 A2 dagger are the same because A1 and A2 commute because they are corresponding to two different modes. So A1 A2 dagger and A2 dagger A1 are the same. A1 A2 dagger minus A1 dagger A2. A1 A2 dagger minus on again alpha 2. I have not specified what psi is. Okay, psi could be an arbitrary state, it could be a vacuum state, it could be a squeeze state, whatever. Now the A2s operate on alpha and A1s operate on psi. Psi is input in the arm 1 and alpha is input on arm 2. Now what is, so I times psi 1. Now what is A2 dagger alpha bra? Alpha star into A1 minus A2 on alpha, alpha A1 dagger. When I open the bracket, A2 dagger is between alpha, A2 dagger alpha, which is alpha star. Because A2 dagger alpha bra is alpha star alpha bra alpha ket is 1. Similarly, alpha A2 alpha is simply alpha. And if I write alpha is equal to mod alpha exponential I phi, this is expectation value of ND is actually I times, so mod alpha let me take out, A1 exponential minus I phi minus A1 dagger exponential I phi. I assume that alpha is a complex number with a phase phi and modulus mod alpha. So alpha star is mod alpha exponential minus I phi, alpha is mod alpha exponential I phi, and so the expectation value of the difference in the signals detected by D3 and D4 is given by this. Now you see, if you choose phi is equal to pi by 2, this becomes expectation value of A1 plus A1 dagger, and that is proportional to X operator. If I choose phi is equal to 0, this will become A1 minus A1 dagger, and this will be proportional to expectation value of Y operator. So by choosing an appropriate value of phi, I can have the signal, the difference current which I am measuring, either proportional to the expectation value of X operator or the Y quadrature. So as I tune my phi, I will measure the corresponding noise in those quadratures. If I choose phi is equal to pi by 2, I will measure the signal corresponding to the X quadrature and the corresponding noise, which I will calculate in next class. So this is very interesting because I am directly measuring the signal corresponding to one quadrature of this field that I am inputting in arm 1. Okay, we'll stop here because what I will do next class is to assume that the input state is a squeeze state, and we will calculate, and I'll show you that essentially what we are measuring is the squeezed quadrature side or the corresponding quadrature which has greater noise than the input, than the squeezed. Okay.